Hello and welcome to this presentation. A shared cache coded caching scheme using designs and circuits of matrices. I am Niladri Das and Professor B. Sundarajan is the co-author. This work was done at Indian Institute of Science, Bangalore. Shared cache coded caching. If you see in the diagram, we will describe what is shared cache coded caching first. Then we will talk about what is a shared cache coded caching scheme. Then we will present our scheme and then the results, the comparison. Okay, so shared cache coded caching scheme, if you see here, there is a server containing n files. At the bottom, if you see, there are capital lambda caches. Each cache can store bits equivalent to m files, and there are in between there are k users. So if you see the link between a user and a cache indicates that the corresponding user accesses that cache. For example, here user 1, 2, 3 accesses cache 1, 3, 4, 5, 6, 7 accesses cache 2, and user k accesses cache lambda. Now all the users can communicate to the server through a shared link broadcast channel. The same diagram over here. If it is mandatory that for each user to access at least one cache. Now, if each cache is accessed by only one user, then the problem is called dedicated cache coded caching, or DCCC in short. If, however, there is at least one cache which is accessed by more than one user, then the problem is called shared cache coded caching. In short, SCCC. Here, if you see, user 1, 2, and 3 accesses cache 1. More than one cache, this cache 1 is accessed by more than one user. So this is an SCCC problem. User to cache association is a list specifying which user accesses which cache. The identity of the users are immaterial, but it matters how many users access each cache. Now, if we will now introduce a notation. If cache I is denoted by Ci, then Li denotes the number of users that accesses the cache Ci. For example, here if you see, cache 1 is accessed by 3 users, so L1 is equal to 3, cache 2 is accessed by 4 users, so L2 is equal to 4, cache lambda is accessed by at least k, user k, so cache lambda, L lambda is greater than or equal to 1. Now it says shared cache coded caching problem has been shown to be equivalent to the multiple file request problem. Now, three phases of an shared cache coded caching problem. First, placement phase. The central server places pieces of the file it has in the caches, and this is done without knowing the user to cache association. User to cache association, each user chooses one of the cache to access. It then informs the server about the cache it accesses, and it also informs the server what is the file that it demands. The delivery phase, in the delivery phase, central server already knows which users are there, which users accesses which cache, and what are the demands of the users, what are the files that the users demand. On knowing that, it broadcast bits of size equivalent to R files. Each user retrieves the file it demands using this broadcast and the contents of the cache it accesses. Now, shared cache coded caching scheme. A shared cache coded caching scheme specifies two things. One, the bits of size equivalent to M files to place in each cache. Two, the bits of size equivalent to R files to broadcast for any possible set of demands made by the users. Now, a terminology. A shared cache coded caching scheme may require each file to be split into a number of subfiles to facilitate placement and delivery. This number is called the subpacketization level. Previous works. The problem was first studied by Madali and Nason in 1. The authors considered the case where each cache serves an equal number of users. Parinillo, Unsal and Elia constructed an shared cache coded caching scheme and showed that their scheme is optimal under uncoded placement. Peter and Rajan in 3 used placement delivery arrays, or in short PDAs, to construct an shared cache coded caching scheme. The authors modified existing PDAs to construct new PDAs suitable for shared cache coded caching. The authors also showed that the scheme in 2 is a special case of their scheme constructed from the MNPDA. Now let us talk about our scheme. To introduce our scheme, we will talk about first a little bit about matrices of circuits of matrices. Circuits of matrices are nothing but minimal dependent sets of rows. For example, let C be a set of row indices of a matrix. If C is a circuit of the matrix, then the set of rows in C are dependent. But for any I in C, the set of rows in C set minus I is independent. For example, let us see this matrix here. G is equal to, has 5 rows, 1, 2, 3, row number 1, 2, 3, 4 and 5. The first 3 rows, if you see 1, 0, 0, 0, 1, 0 and 0, 0, 1. Row number 4th is the sum of all the first 3 rows. Row number 5th is, the sum can be obtained in various different ways, but one can see that it is the sum of first row and the 4th row as well. Now the circuits of G are 1, 2, 3, 4. Why? If you see 1, 2, 3, 4, the vectors are dependent over the finite field that over here we're considering F3 as the finite field. These matrices are over some finite field, and 1, 2, 3, 4 are dependent. But if you remove any of this element, the subset will have is independent. For example, if you remove 1, 2, 3 and 4 are independent, and so on. If you remove 2, 1, 3, 4 are independent. If you remove 3, 1, 2, 3 are independent. If you remove 4, 1, 2, 3 are independent. Likewise, the same would happen for this. If you see here now, this is only 3 containing 3 elements. This is a circuit containing only 3 elements. So 1, 4, 5 is a circuit. Why? Because 1, 4, 5 is dependent, if you see here, but if you remove any one of them, it is an independent set. Now here a point to note here is that if a circuit contains 4 elements, then it is called a 4 length circuit. If it contains 3 elements, it's a 3 length circuit, like here. Set 1, 3, 4 is not a circuit. Why? Because the corresponding rows are independent. Set 1, 3, 4, 5 is not a circuit. Why? Because 1, 4, 5 is not an independent set. If we remove 3 here, 1, 4, 5 that we get is not an independent set. Now let us see our scheme that we have. So this is considered a shared cache correlate caching problem with capital lambda caches, n files, m by n is equal to t by q, but q is a power of prime and t lies in this range 1 to q. Key users. See, the maximum allowed subpacketization level is f max. For n equal to this value, let G be an n times m matrix over fq such that m lies between 2 to n minus 1, rank of G is equal to m, q to the power m is less than or equal to f max, and every element in 1 to n is a member, which means the row indices of the matrix G is a member of at least one m plus 1 length circuit of G. If all these things are satisfied, then for this problem a rate capital R equal to small r by q to the power m files is achievable for a subpacketization level of q to the power m. Now R is given by algorithm 2 shown in the full version of the paper here. Algorithm 2 is quite big, and to go to algorithm 2 one has to develop several define several other quantities. So we have not shown it in this presentation, but we'll give some point overview. Now the placement. Given lambda caches, capital N files, m by n equal to t by q, and let G be a matrix that satisfies the conditions stated in the theorem. Now it can be shown that such a matrix would always exist, like the previous whatever the theorem says. Such a matrix satisfying the conditions stated in the theorem always exists. It has been shown in the paper. Construct a design xg, ag from G. To construct the design, we have used the method which was originally shown by Tang and Ramamurthy in 5. A design is an ordered tuple x, a, where x is a finite set and a is a subset of set of subsets of x, where all sets in A are of same size. The elements of A are called blocks. Now, how this design is used to do the placement is as follows. Let W superscript I, for where I lies between 1 to n, be the n files at the server. Split W superscript I into q to the power m disjoint subfiles W superscript I subscript 1, W superscript I subscript 2, and so on up to W superscript I subscript q to the power m of equal size for 1 less than equal to y less than equal to n. The subscript j in W superscript I subscript j is called the index of the subfile W superscript I subscript j. For a given cache, select t consecutive blocks from the design we have constructed from G, the matrix, in a specific order stated in the paper, and store the subfiles of all files if the index of the subfile belongs to one of the selected blocks. Now this selection of t consecutive blocks is a little involved, so we have not shown also this one over here. Now the delivery. Given the placement and user to cache association, the complete delivery is shown in the full length version of the paper. Here we give some overview. The construction of the design establishes, the design that we construct establishes an one-to-many correspondence between the rows of G and the blocks of the design. Our placement establishes an one-to-one correspondence between blocks of the design and the caches. The user to cache association establishes an one-to-many correspondence between caches and the users. So now combining all three, there is an one-to-many correspondence between rows of indices of G and the users. Now what we do, we select an m+1 length circuit C of G such that the elements of C serves the maximum number of users. How this users and elements of C are connected is that through this correspondence that we state above. Now for this particular circuit, we send a set of symbols where each symbol is a sum of certain subfiles. Now once we do this process, we'll again see how many users still remain observed, and we then again select another circuit which given the availability, given all the circuits, we select a circuit which serves the maximum number of users, and we then again proceed to for that circuit we then again proceed to send a sum of subfiles. Now benefits of our scheme. The subpackaging level of our scheme does not directly depend upon the number of users or caches. For any q to the power m, where m is a positive integer such that m lies between 2 lambda upon q, this comes in a ceiling of this, minus 1, our scheme provides a solution having a subpackaging level of q to the power m. So for this, all these values of m, for any q to the power m as such, we can produce a our scheme can produce a result. This scheme, so this provides a lot of choices to the system administrator in terms of choosing the subpackaging level, which may depend upon external factors such as the underlying communication protocol. Now the benefit number 2 is, in a practical scenario, a cache may be offline during placement phase due to various reasons such as power outage. In our scheme, new caches can be added anytime without requiring any changes to the placement of the existing schemes. Without requiring any changes to the placement of the existing caches. Now benefit number 3, in comparison to the shared cache correct caching scheme given by Parinello et al., which is the optimal one, our scheme has lesser subpackaging level. In comparison to the reduced subpackaging scheme given by Peter et al. In 3, our scheme 1 in some cases achieves a lesser rate for the same subpackaging level, and in some cases achieves the same rate but using a lesser subpackaging level. So let us see some examples in comparison. So consider an shared cache correct caching problem with lambda equal to 9 caches, k equal to 45 users, and user to caching is given as such. Here this L equal to this means that the first cache is accessed by 8 users, second cache is accessed by 7 users, and so on. And for m by n equal to 1 by 3. So if you hear what is happening is that the scheme in 2, the optimal scheme, is achieving a rate of 10.68 files for a subpackaging level of 84. Our scheme is achieving a rate of 13.22 files, which is higher. We are sacrificing on the rate, but we are gaining on the subpackaging level because our subpackaging level is only 9. In comparison to 2, our scheme has lesser subpackaging level. Now see, for the same problem, scheme in 3 achieves a rate of 14 files, which is higher than ours, but the subpackaging level of our scheme and the scheme in 3 are the same. So in comparison to 3, our scheme achieves a lesser rate for the same subpackaging level. Now for the same problem, comparison to this, for the same problem we considered another different value of m by n, which is here 2 by 3. Now here we also observe the same thing. In comparison to 2, our scheme achieves a lesser subpackaging level. So we are sacrificing on the rate. The scheme in 2 achieves a rate of 3.32 files, where on the other hand our scheme achieves a rate of 6.66 files, but there's in 2 the subpackaging level is 84, our subpackaging is 9. In comparison to 3, our scheme achieves the a lesser rate for the same subpackaging level. See, both scheme has the 3 and our scheme has a subpackaging level as 9, but their scheme achieves the rate of 7 files. Our scheme gains on the rate 6.66 files. Comparison 3, consider a shared cache correct caching problem with lambda is equal to 12 caches, k is equal to 18 users, and L equal to, this is the user to cache association, which means the first three caches are accessed by only one user. Next 6 caches are accessed by 2 users, and the next again the final 3 caches are accessed by only one user. Now for m by n we get the following. See, scheme in 3 achieves rate R. Our scheme also achieves rate R. Now scheme in 3 achieves the rate R for the subaggregation level of 27. Our scheme achieves the rate of this same rate for the subaggregation level of 9. Our scheme achieves the rate same as the scheme in the same rate as that in scheme 3, but using a lesser subaggregation level. Now one thing to mention here is that both our scheme the rate depends upon the matrix G. Their scheme the matrix in 3 the rate depends upon the PDA that we constructed. So a valid question is that is there does there exist another PDA where the same rate is achieved for a lesser subaggregation level than subaggregation level which is lesser than 27. So we have scoured all the available PDAs. We have found, to the best of our knowledge, whatever the PDA we could find. We have tried, but we felt this we can use it for this example. Whatever PDA we could find, we have seen that is not the case. But it does not also say that, since we probably do not know all the PDAs that there exist, so we cannot rule out that possibility. Okay, so this is the end of the presentation. Thanks a lot.